So I thought we'd work through one more example of having complex eigenvalues and eigenvectors. Mostly so that I can maybe convince you that whether you do it the way I've been doing it in class here or the way he's been doing it in class, you're going to get the same result. I definitely double checked that earlier today. I was like, oh yeah, it definitely works the same. And I'll kind of show you. I'll talk about how they're a little bit different as far as the approach, but they're really getting to the same place. So let's go ahead and find the eigenvalues so that we can solve the system. I'll point out we are going to be solving the system so that we can solve. And I will say, I really do prefer using X and Y versus X1 and X2. It just feels easier to me to write down. So we're trying to solve the system dx dt equal to 2x minus 2y, and dy dt is equal to 1x plus y. All right, using these as the coefficients of x and y. All right, so our eigenvalues, I think well, I don't know, let's find them. Why say things? So we're going to do the determinant of a minus lambda I. I kind of feel like you should be able to look at this matrix and just write it out. Like you don't need to write 2 minus lambda, -2, 1, 4 minus lambda. You need to be like, okay, it's going to be 2 minus lambda times 4 minus lambda minus -2 times 1. And then multiply it out. We're going to get, you're always going to get a positive lambda squared. That's always going to happen. Sorry about that. And then you're going to get a minus 4 lambda minus 2 lambda, which is a minus 6 lambda. And you're going to get a plus 8 plus 2. And assuming I've done that correctly, this doesn't have any real solutions, right? If you try to factor that, it doesn't factor. If you throw it into the quadratic formula, it's not going to work out. So we still have to throw it into the quadratic formula. Actually, technically, that's not true. You could use the quadratic formula here. You could go a different way if you wanted to. Some people like this. So you don't have to do it this way. But I'm just observing here that since the coefficient of lambda is even, you could do something tricky where you complete the square. And that's not our typical way of solving this, but to me, it almost feels easier than using the quadratic formula. What I'm saying is you can write this as lambda squared minus 6 lambda plus 9 plus 1 equal to 0. And then this right here is going to be lambda minus 3 quantity squared equals -1. So then lambda minus 3 is equal to plus or minus the square root of -1. So lambda is equal to 3 plus or minus I. Technically, you can do this all the time. It's only really convenient to do it if your coefficient of lambda is even. Otherwise, it just kind of gets gross. Or you could use the quadratic formula, right? Quadratic also, you would get, lambda equal to -6 plus or minus the square root of -6 squared minus 4 times 1 times 10 all over 2, which ends up working out to be 6 plus or minus the square root of -4 all over 2, which is 3 plus or minus 2i over 2 is I. Oh, same thing. All right, eigenvalues. Good to go. Let's go ahead and find the eigenvectors. Or at least one of the eigenvectors. Right? We only really ever find one of the eigenvectors. He seems to be partial to doing it the way I've been doing it in the past, where you multiply the matrix by the vector to get the lambda times the vector. That's totally fine. I'll do it that way. So, eigenvectors. So for lambda equal to 3 plus I, and we almost always use the one with the positive imaginary part. I don't know why, other than we have to make a choice. That's the one we choose. So we're going to say that our matrix A, 2, -2, 1, 4, multiplied by the vector we're trying to find, which I would rather write as xy, is equal to lambda, which is 3 plus I, times the same vector xy. He uses V1 and V2. I don't like to use V1 and V2 because I like to call them V1 and V2. Oh well. So then using the first equation, we're going to get 2x minus 2y equal to 3 plus I times x. And the work I would do at this point is I would probably subtract 2x from both sides. I guess I would distribute here. So you're going to have like a 3x plus I times x, and then you're going to have subtracted 2, or not, I don't know.
if negative 2y equal to 3 minus 2 is 1x plus ix, or probably better written, negative 2y equals 1 plus I times x. The only reason to distribute it there is just so you can make sure you subtract the right things when you bring the x over. This is why I don't like doing it this way. I would much rather have done it the other way, but just to kind of show you, you can do it either way. He tends to like to divide by this coefficient of y here. I don't love that choice. I don't think it's necessary. I personally would pick my vector to be x equal to negative 2, y equal to I plus 1. He would probably make the choice to let x equal 1 and y equal I plus 1 divided by negative 2. They are both valid. I would just rather not deal with fractions if I didn't have to. Okay. As an aside here, pens would be good. I will just point out, if you were for some reason asked to find both eigenvectors, there's a real easy thing to do here. For your other eigenvector, well, the other eigenvalue would have been 3 minus I, and the other eigenvector, take every imaginary thing and change its sign. Your other eigenvector would have been negative 2, 1 minus I. That is always true. If you're trying to find both eigenvectors for some strange reason, that's an easy way to do it. You don't have to do any more work than that, which is kind of great. Okay, so we've got our eigenvalue, we've got our eigenvectors. Now we're going to write our solution. I just want to look at one thing. Sure, he does that. That's fine. So for the solution, it's going to be x of t is equal to, I like to write it as c e to the lambda t times v, which in this case is going to be c e to the 3 plus I times t times the vector v, which is negative 2, 1 plus I. By the way, just as a aside here, I was looking at his complex eigenvalues work through that he posted on the week 7 page, and there was a small error in the eigen in the like the end of his solution. In the end of his solution, he's writing cosine of 2t and sine of 2t, and that's actually wrong. It should be cosine of t and sine of t. He accidentally had an extra 2 in there for some reason. I did email him to let him know, so we might fix it, but it's not a huge deal. But if you were looking at that and wondering where that 2t is coming from, it's actually a mistake. So just in case you're curious. Back to this. So what I'm going to do is I'm going to do the way I like to do it first, and I'm going to go back and do it the way he does it and show you that you get the same thing, just so you can kind of see both ways and be fine doing it either way. So what I typically do here is I break this apart, right? It's c e to the 3t times e to the it. Like the mistake he made there, he wrote e to the 3it, essentially, is the mistake that was being made there. Times the vector negative 2, 1 plus I. Replace the e to the it with the Euler's formula thing. So we get c e to the 3t. E to the it is going to be cosine of t plus I times sine of t, all times negative 2, 1 plus I. And after, I'll say, and you'll see this too, after looking at the way he did it, the way he does it might be easier, or might be easier, another word, might be more, there's a word I'm looking for, I can't find, but faster to do. It might require less steps in the way I'm doing. So we'll talk about that in a second. So then multiplying out this part, we're going to get c e to the 3t, and then we're going to have this vector, cosine and I sine are going to multiply negative 2. You should have cosine of t times negative 2 and minus 2I sine of t. And then we have to FOIL out here. You're going to get 1 times cosine. You're going to get I sine times 1. You're going to get cosine times I. And you're going to get I sine times I, which is going to be I squared times sine. And then we break it up into the two pieces. So we're going to have c e to the 3t, and then we're going to multiply that by two vectors. The one with the real parts, which is negative 2 cosine t in the first coordinate here. And the second coordinate, it's cosine t minus sine of t is much better than that square root of 39 problem we were doing last time. Right, it is a minus sine of t because it's cosine t, and I squared is -1 times sine of t over there. And then we have the second part, I multiplied by -2 sine of t. And then we have I sine plus I cosine. So we have sine of t plus cosine of t. You could probably condense some of these steps. The final step here is to distribute to each one. And let me just check one thing here. Sure, yeah, let's write it that way. So if we distribute this to each thing, the C here and the C times I here, we're going to call C1 and C2. So we're going to rewrite this as, and I wish I could have fit this on the page, but oh well. We're going to have C1 e to the 3t times this first vector, -2 cosine of t, and then cosine of t minus sine of t, plus, and watch this carefully here, the c e to the 3t times I, well, c times I is just another constant. We're going to call that c2. Still have e to the 3t, and then the second vector. Sorry. And their vector is -2 sine of t, and then sine of t plus cosine t. That's how I would prefer to solve it. But maybe he wants to see you do it more like the way he does it. So let's talk about how he would do it slightly differently. Starting from where we have our eigenvector. Probably can fit this all on this page. Hopefully. So here's what he would do. He would take your eigenvalue of 3 plus I and your eigenvector of, what was my eigenvector here? -2, 1 plus I. And he's going to break up that eigenvector into the real part of the vector and the imaginary part of the vector. So that's going to be the vector -2, 1 plus the vector. Let me see one thing here. He does factor out the I times 0, 1. And then he kind of does the same work. So we're still going to do all the same things multiplied together. So we're still going to do our e to the lambda t. He doesn't write the constant in front. He kind of saves that till the end. Okay. So our e to the lambda t times v is going to be e to the 3 plus I times t. He's going to break up the vector v as the two pieces, right? It's going to be written as, I think he gave these names in class. I think he called them like U and V or W and V or whatever. I don't do that. I can just write them out. It's not that much of a pain. He actually kind of doesn't write all this out like I'm writing it. He deals with the e to the imaginary part first over here. So let's point out that this e to the 3 plus it is again just e to the 3t times e to the it, and the e to the it part is going to be our cosine of t plus I sine of t. So what we're going to get here is e to the 3t times cosine of t plus I sine of t times these two vectors, -2, 1 plus I times 0, 1. And the next step, really, he's just foiling it out. He's really just saying, well, if I FOIL this out, I'm going to get the real parts, which will be cosine times the real vector and I sine times the imaginary vector, but it's going to change the positiveness to negativeness there. And then the imaginary parts are going to be I sine times that and cosine times that. So check it out. Here's what we're going to get. Yeah, so we're going to get e to the 3t times, I'm going to have cosine times the vector -2, 1. And I'm going to have I times sine times another I is I squared times sine, which is negative sine. So it's going to be negative sine of whatever your angle is times the imaginary part of the vector. That's why you're getting that minus sign there. So whenever you do it this way, it's always cosine, negative sine, and then it's going to be cosine sine over here, both positive. So for the other part, we're going to have e to the 3t times, now we're going to have, let me write through it. We're going to have I sine times negative 2, 1, so it's going to be, oh, and I'm going to pull out the I as well, so I'm going to pull out the I as well. So we're going to have I times sine times negative 2, 1 plus I times 0, 1 times cosine. And again, the I has been pulled out. And then he says, I don't really like writing my answer this way, but he says, call this first part g of t, I think. Yeah. This is g of t. And this part here, without the I, this is h of t. And then our general solution is going to be that x of t is equal to c1 times g of t plus c2 times h of t. But if you look at the vectors we have, hopefully you can see that we've got the same stuff, right? Our c1 times all of this is the same as this, right? Up here you have c1 e to the 3t times negative 2 cosine. Up here you have c1 e to the 3t times negative 2 cosine minus 0. And then for the second part, you have c1 e to the 3t times cosine minus sine. Down here you have c1 e to the 3t times cosine times 1 minus sine times 1. The same thing. Same part over here too as well, right? This piece over here is the exact same as this piece, or I should say, this piece over here is the exact same as this piece over here. So either way you want to do it, you're going to get to the same spot, which is nice because it's nice. To me, this feels a little more awkward personally, but that's just because I've been doing it the other way for so long. So you should do whichever way feels better, unless, well, you should do whatever your teacher tells you to do, really. Like if he says do it this way, then I guess you should do it this way. But if he doesn't really care how you do, as long as you can get there, whatever feels more comfortable should be totally fine. Cool. Questions about that? While we're on the top, well, no, we'll skip that. We'll come back to that. So the other thing I want to talk about today was classifying the stability of our equilibria based on the eigenvalues, which is actually kind of an easier thing than what we've been doing, in my opinion. So there's kind of 6 cases, and you probably all have an idea already of how most of this is going to go. A reminder, when we do this, and you've seen this already, when the eigenvalues are positive or have a positive real part, that means your e to the 3t grows and grows and grows as t gets larger and larger and larger, right? That's going to get bigger and bigger and bigger. If your values are getting larger and larger and larger, they're moving away from 0. They are not getting closer to your equilibrium of 0, 0. So positive eigenvalue or a positive real part of your eigenvalue means we're going to have instability. Whereas on the other side of things, a negative eigenvalue is going to lead towards stability, right? If that was e to the negative 3t, that thing's going to get smaller and smaller as time gets larger and larger and larger. Okay, but let's lay it all out. So here is what we've got. Classifications of stability. I'll also remind you that this is where it's really important that when you're doing these types of problems, you make sure you're reading what the question's asking you to do. Right? If they're just asking you to classify the stability, that is not at all as much work as finding the general or particular solution. So really, really, really make sure you're reading the question about what's going on. So first we have real eigenvalues. So for real eigenvalues, there are 3 general cases. Case 1, if both eigenvalues, which we'll refer to as lambdas, if both lambdas are positive, that means we're going to be unstable, right? We're going to shoot outwards. It's probably going to look something vaguely like, here's one of your eigenlines, here's another one of your eigenlines, and we are moving away from the origin. So if both eigenvalues are positive, we call this an unstable node. And then, yeah, the equilibrium, which so far in every case has been the origin, right? We haven't talked about having other equilibria, which is totally fine. The equilibrium 0, 0 is an unstable node, also called a source, because you can think of everything emanating from it. Okay, or case 2, if both eigenvalues are negative. Well, then everything's going to be pointing inward. Maybe your eigenlines again. Your eigenlines have to pass through the origin. It's kind of the deal. But now we're pointing inward because we're getting closer and closer to 0. And the equilibrium here is going to be a stable node. Also called a sink, because you can think of everything going into the drain of the sink. And lastly, kind of our least desirable case, in my opinion, but that's just my opinion. I don't know why. There's no reason any of these should be more desirable than the others. It just feels like the least good when you get it. If you have one of each sign, so if one of your eigenvalues is positive and the other one is negative, then we have a saddle. It is considered unstable. So I'll point out which is considered unstable. It looks like something like this. You might have one of your eigenlines. The eigenvalues are negative, so we're pointing inwards. The other eigenline, the eigenvalue, whoops, wow, you have to go through the origin, James. The eigenvalue is positive, so you're pointing outwards. If you want to draw like kind of a initial condition and kind of see where you get pointed toward, right? If you have an initial condition for this first one up here, you're going to get pushed away like that or like that, right? You're moving outward. Whereas for this one, the initial conditions always point you inward towards the origin. Or going inward, I should say. But for these ones, the saddles are the most interesting, I think, because when you start somewhere like here, you kind of move towards the origin and then you get pushed away that way. Or if you start somewhere like here, same sort of deal. You get pushed inwards and then outwards. It's kind of like the eigenlines are kind of like attractive forces that push or pull you in whatever direction they're pointing in. And the closer you are to them, maybe the more strongly they do that. I will point out also that for the saddle, there is one direction of stability. So if you happen to start out with an initial condition that sets you on the eigenline that is associated with the negative eigenvalue, then you can end up going straight to the origin. What that would mean is that in your general solution, the part with the positive eigenvalue essentially wouldn't be there when you found your C1 and your C2. Your C1 would be 0. And so you'd only get part of the solution. We can look at an example of that. Yeah, we can look at an example of that in a little bit here. Question?
Is saddle?
No, it is not a no. The saddle is just a saddle. It's kind of similar-ish to when you were finding maxima and minima of functions of two variables and like surfaces, and you were finding relative maxima or relative minima or saddle points. Same kind of idea. There's a very kind of natural relationship between these things and those things. They have a very similar kind of way of thinking about them. So the great thing about all this is you can totally do this purely based on the eigenvalues, right? So for example, if we said, not this times. So for example, if we have the relationship where the derivative of your vector, your solution x is equal to a times x, we want to, sorry, and A is a 2x2 matrix. We want to analyze the stability of the equilibrium. That's a lot of words to say. Find the eigenvalues, look at them, and tell me whether you have a sink, a saddle, or a source. So for example, if our matrix was A equal to, I don't know, -4, 2, -5, 3, we could say pretty quickly, well, all right, so determinant of A minus lambda I is going to be -4 minus lambda times 3 minus lambda minus 2 times -5. Set that equal to 0 and solve. Let's see, we've got lambda squared plus 4 lambda minus 3 lambda is plus 1 lambda. And then minus 12 plus 10 is minus 2. So then usually sometimes these factor, sometimes they don't. So we're going to get lambda plus 2 times lambda minus 1 equal to 0. So we're going to get lambda equal to -2 and +1, which means we have a saddle. So 0, 0 is a saddle. All we have to do, right? There's no other work to do here if we're just being asked to classify this. Okay, I'm gonna give you guys an easy one. So let's say our matrix is 3, 0, 4, 7. You already know the eigenvalues. You should already know the eigenvalues. You shouldn't even write. So I would say, if someone gives you a matrix like this, they're not expecting you to write down anything like determinant of A minus lambda I equals 0. They're expecting you to say, cool, lambda 1 equals 3, lambda 2 equals 7. If they give you a matrix where there's a 0 there or a 0 there, they think you know, okay, great. That means the eigenvalues are just the diagonal entries and we're done. Since they're both positive, that means we have an unstable node. So 0, 0 is an unstable node, also known as a source. And then, sure, one more. So why don't you guys try this one? Let's say I'll give you, no, yeah, we'll make this one less nice. Let's say we have A equal to -3, -1, 1, -6. We'll do this one together because this one is kind of actually gross. So your eigenvalues do not always get to be nice. Sad fact. The determinant of A minus lambda I here is going to be -3 minus lambda times -6 minus lambda minus -1 times 1. Again, I really don't think you need to write down your matrix minus lambda in each of the diagonal spots. I think you can skip that step. Multiplying this out, kind of unlovely. We have lambda squared plus 6 lambda plus 3 lambda is plus 9 lambda plus 18 plus 1 is plus 19. That does not seem great. Let's make sure I'm not making a mistake. I'm definitely not. It definitely doesn't look like it factors, and it doesn't because the way to factor would be multiplying to 19. There's only one way of doing that, and it doesn't add up to 9. So here, our eigenvalues, we're going to use the quadratic formula, although he did talk about in class today a different way of doing this, I think, as well, using the trace and the determinant. It's -9 plus or minus the square root of 9 squared minus 4 times 19, all divided by 2. So here's the question. Are these eigenvalues both negative or one of each? I didn't even say both positive because we know they can't be both positive because you got a -9 over here. So certainly -9 minus this is still negative. -9 plus this, well, it depends on how big this is. In this case, it's not that big, right? 9 squared minus 4 times 19 is like 81 minus 78, I think. 78, 76, which is 5. So here you have -9 plus or minus the square root of 5. And certainly -9 plus root 5 is still very negative. Root 5 is not even close to 9. So these are both negative. Negative. Meaning we have a stable node at the origin. Okay. There are similar criteria if your eigenvalues are imaginary or complex. Let's write those down. So, for complex eigenvalues, so here's the good news. For complex, well, there's a couple actually pieces of good news here. First piece of good news is your complex eigenvalues always come in conjugate pairs, meaning your lambdas are equal to a plus or minus b times I. So one of them is a plus b times I, the other one is a minus b times I. And really, the whole situation is definitely based on just whether your real part is positive or negative. Because as we saw before, just a reminder, e to the lambda t here is going to equal e to the a plus or minus bi times t, which we're going to break up as e to the at times e to the plus or minus bi times t. This part here, this e to the bit, that's going to be your cosine theta plus I sine theta kind of deal, which is just going to give you the oscillating part, which is what gives you the spiraling part. This gives you the spiral. That's why imaginary eigenvalues end up giving you a spiral for your solution, or your whatever you want to call them. Whereas this part here, this is telling us if you grow or decline, right? If a is positive, we're going to go to infinity. If a is negative, we're going to go towards 0. So that's why we can see, oh yeah, we're going to get stability if the real part is negative, and we're going to get instability if the real part is positive. And that's kind of almost the entire story. If a is positive, then we have, or then I should say, then 0, 0 is an unstable spiral. Let's see if there's more into this right here. Not really. So another thing about this is solutions oscillate because of the imaginary part or spiral and grow. Right? Oscillate because of the e to the bit, grow because of e to the at, where a is positive. I'm never great at drawing these. It's not so I could certainly draw a spiral for you. Ooh, look at the spiral. And we're going away from the origin. So we're getting bigger and bigger and bigger. But X and Y are going back and forth between being positive or negative, right? That's why we're not just going like straight out where X and Y both say positive, X and Y both say negative, because we have this oscillating thing with cosine and sine. Or if the real part is negative, then 0, 0 is a stable spiral. Our solutions oscillate and dampen. Again, we're dampening because a now is less than 0 instead of a being greater than 0. And I could draw another spiral, but I don't think there's much point because it's just going to look the same, except the arrows are going to point inwards. Fine, I'll draw the spiral. So I'm going to draw it the same sort of way. I'm just going to make my arrows go inwards. I've just made up the direction of spiraling, though. We actually don't know if it's clockwise or counterclockwise until we do a little bit more inspection. And then lastly, if the A part is equal to 0, meaning your eigenvalue lambda is purely imaginary. Underlining my names here. Then 0, 0 is, what is it called? It's called a center or a neutral spiral. Yeah. Is a neutral spiral. Meaning it's not going to dampen or grow. It's just going to keep spiraling in the same loop. It kind of looks like a circle or an oval. So it's also called a center. Yeah, so no growing or dampening, just keep oscillating back and forth, back and forth, back and forth, because you're only getting the cosine theta plus I sine theta part, and the other part isn't there. So this is going to look kind of like, sorry, you've got some sort of just, you're always going around in the same loop. You're never going further away from the origin, you're never getting closer to the origin. You're just doing the same thing forever and ever. Again, it's all based on what your eigenvalues are doing. You don't have to find the solution at all, you just find the eigenvalues. Question? This is center. Sorry about that. Yeah. It's called a neutral spiral or a center. I don't know why they call it a center personally. Like, I'm not sure where the idea of that name comes from, but that is what they call it. So did your teacher talk at all about saying whether it's clockwise or counterclockwise for a spiral? Okay. We won't worry too much about it for now. It's not, so I mean, again, we have talked about finding eigenvalues. You guys are good at finding eigenvalues. It's not that terrible. So for example, if my matrix or if my system had the matrix A equal to 2, -3, 5, -2, let's find the eigenvalues. And we'll talk about how another way of doing this actually. So our determinant of A minus lambda I, it's going to be 2 minus lambda times -2 minus lambda minus -3 times 5. Simplifying this, we get lambda squared. You always get lambda squared, by the way. It's just always a good starting point. It's always lambda squared. And then plus 2 lambda minus 2 lambda. That's interesting. So 0 lambda. Am I doing that right? Yep, I sure am. Minus, maybe this is not the example I wanted to go with. Oh, well, let's play. -4 plus 15 equal to 0 gives me lambda squared plus 11 equal to 0. The nice thing about this is that we don't have to use the quadratic formula here. We can just bring the -11 over to the other side and say, great, lambda is equal to plus or minus the square root of -11, aka lambda is equal to plus or minus I times the square root of 11. What's the real part here? It's 0. The real part is 0. So since the real part of our eigenvalue is equal to 0, that means we have a stable, a neutral, that's a terrible mistake there, a neutral spiral. Yeah, let's go ahead and let's take a quick look, just because I would like to show you what it looks like. I think it is worthwhile to see this one specifically. One moment. I did figure out what I was doing wrong the other week when I was trying to graph that thing. It was coming out super wrong. It just had like a really kind of big period. So like it took a long time for it to actually loop back around in the spiral, but it did spiral eventually. It just didn't look very spirally. This one here, we have 2 times x minus 3 times y. And then we have 5 times x minus 2 times y. If we graph the phase plane, it looks like that. And if you click on any point, you can see that it doesn't spiral out or spiral in. It is a loop that just loops back on itself. So it really, really is a neutral spiral, also known as a center. Okay. Let's look at one more. Yeah. So what I really want to say is, I don't love this example for that. Let's do one more. Let's say we have one more example. Sure. Not you. Sure, you're fine, actually. Let's look at, say, the following. Our matrix is 2, -5, 2, 1. We'll find the eigenvalues quickly here. Determinant of A minus lambda I is going to be 2 minus lambda times 1 minus lambda minus -10. That's going to be lambda squared minus lambda minus 2 lambda is minus 3 lambda plus 2 plus 10 is plus 12. That doesn't factor, so we're going to get lambda equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2, which ends up being 3 plus or minus the square root of 9 minus 48, which is -39 all over 2. I feel like I wanted something else to happen here, but I made it. Oh, yeah, no, not at all. I'm totally not crazy at all. So that's going to be 3 halves plus or minus I times root 39 over 2. Which means we definitely have an unstable node. Unstable what? God, killing myself over here. What do we have to have since the eigenvalues are imaginary? A spiral, not a node. Sorry. Something I want you to see. So I want to point out that for this matrix here, actually, let me write this down here. So for this particular matrix, there's another way of watching for any matrix. There's another way of doing this, where if you look at this matrix A, which is 2, -5, 2, 1, there's a couple quantities about this matrix that always show up in this quadratic equation. Specifically, the trace of A, which is often written as the letter tau, is the sum of the diagonal elements. In this case, it's 2 plus 1, which is 3. And the determinant of A, which is often written as the capital letter delta, which is the usual determinant. It's 2 times 1 minus -5 times 2, which in this case is 2 plus 10, which is 12. Those numbers definitely show up in your equation here, which this is actually called the characteristic equation, lambda squared minus 2 lambda plus 12 equals 0. More generally, the determinant of A is always going to equal the following. It's going to be lambda squared minus the trace times lambda plus the determinant, which in this case, yes, is lambda squared minus 3 lambda plus 12. Oh, look, it's exactly the same equation we had up here. But this is always true. So if you just look, so instead of doing the work of actually writing out lambda minus something times lambda, or something minus lambda times something minus lambda minus the other two things multiplied together, you used to be like, cool, the trace is 3, the determinant's 12, you're going to get lambda squared minus 3 times lambda plus 12, and skip to that. And then we can say that our eigenvalues, we set this equal to 0, here's the general formula. The eigenvalues are going to equal -b, while our b value is the negative trace. Right, there's our b. Our a value is 1. And there's our c there. So using the quadratic formula in this general way, we get that lambda is equal to -b, which is negative tau, which is tau, or the trace, plus or minus the square root of b squared, which is negative tau squared. I'm going to ignore the negative there because if you square a negative, it still turns out positive. So it's tau squared minus 4 times the determinant times 1 all over 2. So here's what matters. There's kind of like 6 things that can happen here. this is going to be real if tau squared is bigger than 4 times delta, the determinant. This is going to be imaginary if the other thing is true. Tau squared is less than 4 times the determinant. What about if tau is positive? Well, if tau happens to be positive, we're going to get instability. Well, I should say, let me give you a heading to this if tau is positive. Below this is all under the guise of if your determinant is positive. Sorry. If your determinant is positive. So if your determinant is positive, then you either get stability or instability. And we'll talk a little bit more about this in a second here. If tau is positive, well, we know that if your real part is positive or your eigenvalues are positive, that means we have instability. Just like in this previous example, right? In this previous example here, we had our trace being positive 3 and our eigenvalues both had a positive real part. It was unstable. So if tau is positive, you get unstable. It's either a node or a spiral based on if your eigenvalues are real or not. And if tau is negative, it's going to be stable. There's one other case I haven't talked about. Or there's one other thing I haven't mentioned yet, really. When do you get a saddle? Well, you get a saddle if your determinant is negative. And I think there's a really cool way of seeing this. Check this out for a second. If your determinant is negative, then tau squared minus 4 times your determinant is going to be more positive than it was before. So check this out. All right, let me write this down because I think this is actually really kind of worth seeing here. So note, if delta is negative, determinant's negative, then tau squared minus 4 times delta is bigger than tau squared. And then if you take the square root of both sides, the square root of this is bigger than the square root of tau squared, which is bigger than tau. Or more negative than negative tau if it's a negative number. But here's the point. Check this out. If this part right here is bigger than tau, then tau plus that and tau minus that, one of those has to be positive, one of those has to be negative. Right? If you take 3 and do plus or minus 4, you're going to get a positive thing and a negative thing. So if you have a number and you add and subtract something that is larger than it, you're always going to end up with one positive thing and one negative thing, which means we're going to have eigenvalues of opposite signs. It can't be imaginary. So we have to get a saddle. Kind of cool. There is a really neat picture in your book, I think, that kind of describes all this, which is this picture here. So let me zoom in here so you can actually see that a little bit better. So this picture shows you that if you make your x-axis the value of the trace and your y-axis the value of the determinant, well, if your determinant's negative, you're down here in saddle land. If your determinant is positive, you have either stability if your trace is negative, instability if your trace is positive, and then depending on whether your determinant is big enough or not, you get spirals or you get nodes, right? If your determinant is larger than 1/4 the trace squared, which just corresponds to whether or not this quantity here is positive, right? If the trace squared is bigger than 4 times the determinant or not. So you can't see it all what I'm pointing to. Apologies. Just right, that's the same thing as that. We're just saying here, right, that the determinant is less than the trace squared over 4 or the determinant is bigger than the trace squared over 4, then that's the kind of the dividing line between having spirals and nodes. All right, that's all the time we have for today. We'll definitely talk more about this on Friday as far as these classifications, but really the classifying is really easy for these. Just find the eigenvalues. Sometimes it's kind of gross and sometimes it's easier just to look at the determinant and the trace of the matrix, but you don't have to really ever do it that way, usually. It does come up more if we start talking about non-linear differential equations and looking at the multiple equilibria and trying to kind of classify around each equilibria what kind of behavior we have. Then you kind of do need this idea with traces and determinant. So if we go in that direction, which is optional, I'll look out for that. We'll talk more about it. All right, that's all. You're free to go.